So, problem states, for the parametric equations, determine the standard xy rectangular equation. State the initial point of the curve, indicate the orientation of the curve, and sketch the curve. Our first job, it says, is to determine the standard xy. We need to eliminate the parameter. So we are going to solve one of the equations for t and plug it into the other equation. Let's simply go ahead and solve the top equation for t. Subtracting 1. Dividing everything by 8. Then rewriting. We simply plug this back in to the other equation for t and simplify. Distributing. Simplifying as we go with our fractions. Double negative makes a positive. And now we combine like terms. 3 is 6 halves, so it's going to be 7 halves. And there's our regular xy equation. Now, we can go ahead and just graph that line. However, that line is not all of this, because this is parametric, and so generally t is going to start at 0 unless otherwise told to us, and so we want to start t at 0. So in order to state the initial point of the curve, that's going to be when t equals 0. And in order to sketch the curve, we're going to want a small table of points, which are these points on this, but we need to know where that initial point is. Then we can draw the rest of the line. So let us make a table of values. We'll start with t here, x and y. And t needs to start at 0. Plugging 0 in this equation, when t is 0, x is 1. When t is 0, y is 3. We don't need to show our work here, pretty simple. And then let's just pick other values of t. We'll count by integers, 1, 2, and 3. This should give us enough points for a line. Plugging in t equals 1, x equals 9, and y equals negative 1. Plugging in 2, we now have that we're up to 17 for x, and y is 3 minus 8, which is negative 5. When we plug in 3 for t, then we get 25 for our x value. And when we plug in 3 for t in the y equation, we get 3 minus 12, which is negative 9. We now have points, and we can sketch the curve. I'm not going to sketch it here, but you now have points. These are xy points 1, 3, 9, negative 1, 17, negative 5, and 25, negative 9. And if you want, you could verify that in our xy equation. Moving on to another problem similar to this. Oh, hold on. Back up. It wants to know the orientation of the curve. So we know that this line is a line that moves down and to the right because it is decreasing. So it's going to start at the point 1, 3 and move down and to the right. That's where it's going. That's what we talk about. All right, let us move on to another problem. Okay, so this is warm-up number 2a. And same thing. For the parametric equations, determine the standard xy rectangular equation, state the initial point, indicate the orientation of the curve, and sketch the curve. So again, these are linear, and when we combine two linear parametric equations, we're going to get an overall linear equation. So let us solve one of these for t, and we'll plug it into the other one. Solving the x equation for t, we're simply going to divide both sides by 4. So t is equal to 1/4 x. And we're now going to plug that into our y equation. Y is equal to 2 minus, I'm going to rewrite 0.5 as 1/2, because fractions are our friends. And then we're going to plug in the 1/4 x. Simplifying. And writing it in y equals mx plus b form, we have our xy equation. Similarly, as we did in the last problem, we're going to make a table of values to get our initial point and some points that we could use to graph the line. So, t, x, and y in our chart. And of course, we're starting with t equals 0 unless told otherwise. So t equals 0 here. We're going to now plug that in when t equals 0, x equals 0, but y is equal to 2. Okay, choosing 1, 2, and 3, we are now going to plug 1 in. Our x value is 4. Plugging 1 into the other equation, it's 2 minus 0.5, or 1.5. I'm going to write it as a fraction, which is 3/2. Plugging in 2, x is now equal to 8. And plugging in 2 times 0.5 is 1, 2 minus 1 is 1. Plugging in 3 into each equation, 4 times 3 is 12. And then plugging in 3, you get 3 times 1/2 is 3/2. 2 minus 3/2 is 4/2, minus 3/2, 1/2. And again, we have our initial point. And we have 3 other points that we could use to sketch the curve. Again, looking at this equation over here, y equals negative 1/8 x plus 2, we realize that that equation is also moving down and to the right, a lot slower than the previous one, but still, we start at the point 0, 2, and we move down and to the right. Let us move to another sample problem out of the book. Okay, this problem is problem number 1 on page 650 out of the big L, Larson. And again, we're going to sketch the curve represented by the parametric equations and write the corresponding rectangular equation by eliminating the parameter. Here they kind of want us to do it in reverse order, but it doesn't really matter. We're going to do the same as before. Let us solve for t. And I hope after doing these 3 problems that by exhaustion, we kind of get what's going on with linear equations that are parametrized. Okay, so solving one of the equations for t, I'm going to solve, of course, x. Doesn't really matter. You can solve the y equation if it looks simpler. But x equals 2t minus 3, add 3, divide everything by 2, and so t is equal to 1/2 x plus 3/2. Let's plug that value t into our y equals equation, and we have y equals 3 times 1/2 x plus 3/2. Distribute and simplify. This is 3/2 x plus 9/2. And we have our xy equation as before. Okay, again, making a table for t, x, and y. And of course, not told otherwise, we are going to start at 0. This is our initial point again. And so let's mark that that's going to be our initial point. Let's plug in 0 into both equations. We get negative 3 for the x, and we get 1 for our y. Plugging in 1, 2, and 3 separately. Plugging in 1, we get 2 times 1 is 2, minus 3, negative 1. plugging in 1 into the y equation, we get 3 times 1 is 3 plus 1 is 4. On to t equals 2. 2 times 2 is 4. 4 minus 3 is positive 1. In the y equation, 3 times 2 is 6 plus 1 is 7. And plugging in 3, we get 6 minus 3 is 3. Of course, you can see that we've developed a pattern. Each parametric equation is linear, so you can just go with the patterns that you see. We're increasing by 3, so this one over here should be 10. And again, you have points that you can plot. This is moving up and to the right, since it happens to have a positive slope. Starting at the point negative 3, 1, we are moving up and to the right. All right, let us move on to another sample problem out of Larson. And now, problem number 15 on page 650 out of the big L. And this one says, sketch the curve represented by the parametric equations, again, and write the corresponding rectangular equation by eliminating the parameter. And you say, holy moly, what do we do with this one? Suddenly, this isn't linear. So we have to decide what we need to do. If this was just sine and cosine, we might have a better idea. We might use the equation for we would use the equation for the Pythagorean identities out of trig, but this is not sine and cosine. This is secant and cosine. So, as a hint, let's try and write everything in terms of sines and cosines. It might help us. So, x is equal to 1 over cosine theta, and y is actually equal to cosine of theta. So, these are merely reciprocals of each other. So, replacing cosine of theta in the original equation with y, let's rewrite. X is now equal to 1 over y. Writing it as a function, y is equal to 1 over x, or x times y is equal to 1. That's written as a hyperbola. And that, of course, is the hyperbola with asymptotes that are the x and y axes. So y equals 1 over x is our curve in rectangular form, and we're going to go ahead and sketch it now. Please note the change in domain here. We can't just plug in anything for theta, so we need to be careful, and we need to talk about the orientation of this thing as well, what's going on. So, looking at starting at 0 for theta, and theta is just like t, so don't get caught up in the fact that it's theta. It's a parameter. T can be a parameter at time. Theta can be a parameter talking about an angle. So again, don't get too caught up in the fact that it's theta versus t. It's just a variable that's not x and y. Okay, so we have theta, we have x, and we have y. It says that we have to start at 0. So using 0 there for our theta, plugging that in. 0 into cosine. Cosine of 0 is 1. So secant is 1 over 1, which is 1. And of course, the y value is just cosine of 0, which is 1. Okay, let us move. We need to pick some nice values of theta. Let's move to pi over 6. And we pick pi over 6. Cosine of pi over 6 is the square root of 3 over 2. So then, secant is the reciprocal of that, which I'll just give it to you in rationalized form already. That's going to be 2 over the square root of 3, but multiplying top and bottom by the square root of 3, we get 2 square roots of 3 over 3. Okay, pi over 4. And when we plug in pi over 4, we're going to get the square root of 2 over 2. The reciprocal of that, the square root of 2 over 2, would be the square root of 2. 2 over the square root of 2, 2 square roots of 2 over 2. The 2's cancel, left the square root of 2. pi over 3. Plug in pi over 3, we're going to get 1/2, and the reciprocal of that is 2. So we have an idea here. We cannot plug in pi over 2. So, because pi over 2 into secant doesn't work, gives us an undefined point because we're dividing by 0. So we will then move to 2 pi over 3. So this is y equals 1 over x, but since we can't plug in pi over 2 in for t, and that's very specifically, or in for theta, theta definitely does not equal pi over 2. We're going to get a hole in the graph here. Okay, we will get a hole in this graph. So as you can tell, what we're doing with y equals 1 over x, we are moving from the point 1, 1. So we're starting at 1, 1. We're not starting anywhere else on this curve. We have to start, we can't start at 0 because obviously that's undefined. So we actually, when theta is 0, the point is 1, 1, and we've got the remainder of the curve. And you can see that there. So this would be 1, 1. And that's the part of the curve that we get. But still, plugging in the remainder of these points, I'm going to plug in 2 pi over 3, 3 pi over 4, and 5 pi over 6. And so, plugging in those points, cosine is negative now, so that's negative 1/2. And then we will get negative 2. Now wait a second. These points are where? They're on the other side, aren't they? So as we get closer to pi over 2, we get that horizontal asymptote when we go out to infinity on the xy curve. But then when we get 2 pi over 3, now we're on the other piece. We're on the other side of this. Interesting. So 3 pi over 4 is going to give us a negative square root of 2 over 2. It's also going to give us then the negative square root of 2. Similarly with 5 pi over 6, negative square root of 3 over 2. And therefore negative 2 square roots of 3 over 3. And that part of the curve is on the other side over here. And so we're going to get that piece. Interesting. Don't get the entire curve because that's just what happens. All right? Problem number 51, page 650 in the big L. Now, this wants us to go backwards. They've given us the xy equation. We need to get a set of parametric equations. Now, there are many that we could write. In general, we will use the form that's up here. X equals x sub 1 plus delta x times t. Y equals y sub 1 plus delta y times t. Now, delta x and delta y are going to come from slope. And since the slope can be represented with multiple fractions, not necessarily reduced to lowest terms, therefore, there can be multiple representations of this. We'll make it simple on ourselves. The slope of this is 2, so I'm going to write this as 2 over 1. And delta y will be 2, while delta x is 1. From the point that they give us, x sub 1 is 3, and y sub 1 is 1. And simply plug these in. X is equal to x sub 1, which is 3, plus delta x, which is 1, t. Y is equal to y sub 1, which is 1, plus delta y, which is 2, t. This is one set. And definitely has the initial point or the point 3 comma 1, the initial point 3 comma 1. When t is 0, x is 3, and y is 1. And that's as simple as it gets. But let us remember these equations right here. Those will be important. You should copy those down in your notes. We will conclude with more on the next video, where we will work out of the Finney book.